In our Mobile Studio's Graphics Analyzer, you can see all the graphics API calls that the application made and step through them one by one to see how the scene is built. In the previous section, we learned from the streamline capture that some parts of the game could contain objects that are too complex for their on-screen size and distance from the camera. Let's take a capture with Graphics Analyzer to explore the scene in more detail. Start by opening the Device Manager. If your device is connected via USB and you have ADB installed correctly, you will see the device in the list. Here we can see the list of applications installed on the device. Note that we can only capture data from debuggable apps. We select the game that we want to profile and start the capture. The game starts automatically on the device and Graphics Analyzer starts capturing frames. Keep an eye on the game as it's running on the device, and when you get to a scene you want to explore, press pause. For frames of interest, we can capture extra information to help evaluate the scene. Select the camera icon to capture the frame buffer output at this frame. Next, let's capture the overdraw in this scene. Select Overdraw mode, then click the camera icon again. Use the play, pause and step controls to move the game onto a different scene. You'll notice that the game runs slower than real time because frame data is being collected, which does slow things down. Here we will capture the shader map. This shows your shaders in a different colour so you can see where they are used in the scene. Lastly, let's capture the fragment count to see how many fragments were drawn by each shader in the scene and how many GPU cycles were spent drawing each shader. When you've captured enough data, stop the capture. Here we can see all the graphics API calls for every frame in the capture. Select this option to filter the list to just the frames where we have captured extra data. Frames with the camera icon indicate where we've captured the frame buffer output. Let's look at the geometry in this frame. We know from looking at the Performance Advisor report and Streamline Capture that some of the geometry in this scene could be too complex for its position on screen. Expand the frame to see the render passes that are used to build it, and expand a render pass to see the draw calls. Open the Vertices Geometry view so we can see the object mesh for the selected draw call. From here we can step through the draw calls to see how the scene is built, looking for any problems with rendering order or objects that seem overly complex. These brickwork panels, for example, around the outside of the scene are built with geometry, each using 2064 vertices. The detail is not very visible in the final output, so this is wasted processing. It would be much more efficient to use normal maps here to represent the bumps and angular edges, rather than building it with triangles. The floor tiles have the same problem. These are 1170 vertices each. Even when they are close to the camera, the scene doesn't really benefit from this complexity. Additionally, we can see that these scenery objects are drawn using separate draw calls. We could reduce the number of draw calls by batching these objects together, which could significantly reduce CPU load. Remember that reducing complexity for lots of similar objects adds up to a huge saving in geometry processing, which then subsequently reduces the amount of fragment shading required. Not only will this increase our frames per second, but it will also save power budget and DRAM bandwidth. Here's another example. The statues at the rear of the scene use 6,966 vertices. You can see that the mesh is quite complex, which will give a great visual result when the player gets close to the statues, but from this camera position they are hardly noticeable. Using different mesh LODs to represent these objects when they are this far away from the camera would save a lot of processing power. You really only need to use just enough triangles to preserve the silhouette edge of the object. Earlier, we took an overdraw capture of this frame. The wider the area, the more overdraw is present. Overdraw can be a common problem where UI elements are laid over a 3D scene, so it's good to check how much overdraw is occurring and remove it if possible. Remember, you can reduce overdraw by drawing the opaque objects from front to back and any transparent ones from back to front. The shader map capture is helpful to check which shaders were responsible for colouring in different areas of the screen. Shaders that colour in the largest areas are good candidates to optimise. This also helps you to detect problems where incorrect shaders have been assigned. The fragment count capture gives us extra information about the number of fragments drawn by each shader. We should try to optimise expensive shaders by reducing their complexity or by reducing the number of fragments they have to process. In the next section, we'll explore shaders in more detail using Mali Offline Compiler.